recording. I record all of these, and let's see, I'll want your email address. What is your email address, Sonia?
Okay, it's Sonia, SONJA, dot KLIMCZAK.
Ooh, KLI, is that your last name?
Yes.
Let me just take it off of the KLIMCZAK.
Uh-huh, there it is.
Well, I bet you've had to spell that a lot in your life.
Yes.
Okay. At what?
At gmail.com.
Okay.
Wait, but did you get the 12? It's sonia.klimchek12 at gmail.com.
Oh, no. Wow. You needed to put a number after that even, huh?
Yeah.
I'm surprised. I wouldn't think there'd be that many Sonia Klimcheks. Okay. So what would you like to go over? Now, originally when your mom talked to me, she said you were also preparing for the SAT?
Yes, I am.
Okay. I have a bunch of SAT practice tests on my computer. So if you want to ever have a session with SAT, I can provide all of that material.
Okay, awesome. That sounds good.
Okay.
But for today, I was thinking, because I have a math test tomorrow,
Okay.
so there were just a couple of things I wasn't sure on.
Okay, let's go over them.
Okay, so right now I'm doing things like graphing functions and no, not functions, but like
Rational quotients, probably. Why don't you read the function and we'll...
Okay. Okay. So, finding things like finding the remainder r when f of x is divided by g of x, and is g a factor of f. So, like, one of the numbers is f of x equals 8x to the third minus 3x squared plus x plus 4, and then g of x is x minus 1.
Okay, and they want to know what f of x divided by g of x is?
Yeah.
Okay, do they want you to do this with synthetic division or long division, or does it matter?
I don't think it matters.
Have you studied synthetic division?
Yes, I know what that is, yeah.
Okay, let's use synthetic division. Although it's also important to know how to do long division.
Right.
In other words, just real quickly, I'll show you how to do the long division, just the first couple steps, and then we'll go through and do it synthetically. First thing you do is divide that into that, if you're doing it long division. Okay, well, that goes 8x squared. Then you multiply that by both terms. So you end up with 8x cubed minus 8x squared, and you just proceed using long division like that.
Okay.
Okay, now synthetic is a little bit easier. You don't have to worry about the variables. As long as you remember what to put in the box.
Okay.
Those are the coefficients of f of x. Now, do I put minus 1 or plus 1 in the box?
You would put plus 1.
Right. You put the solution to that, which is the opposite sign of that. So you always put the 0 in the box, okay? You want to work me through the synthetic solution here?
So you would do it 1 times 8?
Well, not really. What you really do is bring down 8. Now 1 times 8, and you put it there.
Yeah.
And now it's adding instead of subtracting. So you
So 5.
kind of think of it as originally when we did it long division, we were subtracting every time. But
Yeah.
now we changed the sign on that, so we're going to add. And that's easier just because addition's easier than subtraction. So what next?
5. And then 5 times 1 is 1. And then 6. And then bring it down, and then it's 10.
So that is your remainder. So what's
Right.
the answer?
So the answer would be
Well, reading the synthetic division, reading my bottom line tells you the answer. What is it?
8x to the second
Huh?
plus 5x plus 6 remainder 10.
Plus 6x.
All right.
And the remainder is 10 over x minus 1. In other words, if you had to express it as more than just a remainder, in other words, you can say remainder 10. I don't know if that's the answer she's looking for or not. But what that means is 10 divided by the divisor. And the divisor was x minus 1.
Wait, but wouldn't it be 8x squared plus 5x plus 6?
Plus 6x.
But why is it 5x squared instead of just 5x?
My mistake. Excuse me.
That's okay.
In other words, because we have every factor of x represented there, 3, 2, 1, we're going to have everyone represented down here, and it's going to go 2, 1, 0. I just made a mistake of writing the 1 or the 2 there.
That's okay.
Yeah, no, that's absolutely correct. Thank you.
Yeah. I also had, I had another question. So another part of the chapter is like analyzing the graph of a function.
Okay.
And so, for example, like a problem would be like x plus 1 over x times x plus 4.
X plus 1 over x plus 4?
No. X times, in parentheses, x plus 4. But that's on the bottom. The top was right. It's x plus 1 over x times x plus 4.
Okay. Like that?
Yeah.
Okay. Well, the first thing you want to do whenever you're graphing something that looks almost hyperbolic is determine where your asymptotes are. Where I've got what two values for x are outside the domain?
I'm not sure.
What makes the denominator 0? That's what you can never do. The first rule of math is you cannot divide by 0.
Yeah.
So if x were 0, we'd be dividing by 0. Or if x were minus 4, we'd be dividing by 0. So that's where our two asymptotes are. I have a vertical one at x equals 0, and I have another vertical one at x equal minus 4. Okay.
So it could not equal 0?
Exactly. Because if x were 0, the denominator would be 0. Anytime you have two things multiplied, one of them 0, then the product is 0.
Oh, and then if it was -4, then it would be
plus 4.
Oh, then it would cancel out, and so it would be 0 times -4, and it would still be 0.
Right.
Okay.
In other words, 0 times anything is 0. So you can't have either that term or that term be 0.
Okay.
If there were 3 or 5 or 7 terms in the denominator, none of them could be 0. And that's what determines your vertical asymptotes. There are are some exceptions to that. In other words, if I had an x plus 4 in the numerator and that I could cancel out, then that vertical asymptote turns into a whole. I presume you've learned about vertical asymptotes, horizontal asymptotes, and wholes.
Yes, but I'm not sure about the wholes again, because my teacher was saying something like if the numerator is squared or something. I don't know.
I'll give you an example of where you would have a whole.
Oh, right. If you factored one of them, and then one of them would cancel out.
Right. In other words, I can cancel this, and it makes it look like the answer's got to be x minus 1. But I have to carry forth the restriction that x can never be negative 1. So that's not quite the answer. The answer is x cannot be negative 1, which means there's a hole at negative 1. There's not a vertical asymptote, but there's a hole. And
Wait, but wouldn't it be x cannot equal 1? Because if you plug in 1 for x, then be 1 minus 1 is 0.
Well, we're looking for what would make the denominator 0. I don't care if the numerator is 0. That's okay. Okay? But the denominator is what cannot be 0, and what makes it 0 is an x of minus 1.
Oh, okay.
Okay? It's just that we cancel it out, and it looks like the answer is x minus 1. Well, if I were to graph x minus 1, I'm going to use the same graph as this other function here. There's the graph of x minus 1. It's a straight line, but there's a hole right there.
Oh, okay.
At x equal minus 1 because of that restriction in the domain. In other words, it would look like that. Now, if in fact you feed this into a calculator, this whole thing right here, no matter what kind of calculator you have, it won't show you that hole. Because notice that that hole is microscopically small.
Yeah.
In other words, it's only 1 point on the number line out of an infinite number of points between 0 and minus 2. So it's not going to show up on a graphing calculator. It's just going to draw right over it and ignore it. Okay, so always know that. In other words, if you're looking to check a calculator, it's not going to do you any good. But that hole is there, and when you graph it manually, you do put the hole in to show that it exists.
Okay.
Okay. As far as this other one, let's take another look at this one. So I've determined the two vertical asymptotes. Now, what about horizontal asymptotes? There are 3 rules for horizontal asymptotes. Okay? There's the case where that power is smaller than that power, and it does not matter what else follows. I mean, I could have 1,000,000x or 100x, it doesn't matter. And same thing up here. I could say I got 1,000x. The only thing you care about is that that 2, the highest exponent in the numerator, is less than that 3.
Okay.
That tells you that you have a horizontal asymptote at y equals 0. Okay? That's one situation. And it doesn't have to be 2. Doesn't have to be 2 and 3. It just has to be bigger in the denominator than it is in the numerator.
Wait, but why is it at y equals 0?
That's where it ends up being.
But why? Is it always going to be like that?
As long as the denominator is a bigger polynomial, higher degree polynomial than the numerator, then the horizontal asymptote is always at y equals 0.
Oh, okay.
Okay? And I'm going to cover another situation. The other situation is where they have matching. let's say I had this. In other words, the highest degree here is x squared, the highest degree down here is x squared. Then the horizontal asymptote is y equals whatever the ratio of the coefficients are.
Oh.
So in the example that I've drawn, the horizontal asymptote would be there at y equal 3.
Okay.
Just whatever that ratio is. If that was like that, it would be at y equal 3/2.
Okay.
Okay? And there's only one other situation that you have to contend with, and that is when the top is bigger than the bottom. Like that. And once again, it doesn't really matter what else is there. When you're dealing with these asymptotes, it's only the highest degree in the numerator and the denominator that matter. Nothing else matters. Whether you're taking limits as x goes to infinity or whatever. But when the bottom is exactly one less than the top, then you do the long division. You take x squared minus 1 and you divide it into x cubed plus 4x, and you end up with a linear. Notice the x squared is going to go into the x cubed just x times.
Yeah.
And maybe you end up with that, with some remainder. You don't care what the remainder is, but what you have is an oblique asymptote defined by what I have circled there.
Okay.
In other words, you've been taught oblique asymptotes, right?
Yeah. Yeah.
Okay, so you would have an oblique asymptote like that. And what an oblique asymptote means is that as x goes to infinity, it's going to go to infinity also, the y value.
Okay.
And instead of some horizontal asymptote. Now, here's the thing about asymptotes. Another thing's very worth remembering. The graph can never cross a vertical asymptote. It can cross horizontal asymptotes, and it can cross oblique asymptotes. Okay. It would be perfectly reasonable if I had an oblique asymptote here for the graph to do something like this. Hold on. Excuse me. Maybe it approaches that asymptote, but maybe it crosses that one and then comes back and approaches it. So you can cross both oblique and horizontal asymptotes. Similarly, if I was down here, I could do something like, oops, cannot cross a vertical asymptote though. Ever.
Okay.
Because to cross a vertical asymptote would be saying x could be that value. Mm-hmm. And the thing we know is that x cannot be that value.
Right.
Okay, so let me get rid of all my asymptotes here that don't apply to this problem. We've only got these two, or these three. We got two verticals and we got a horizontal. Now, with a graph like this is hyperbolic in nature. Okay?
Oh, wait, sorry. Hold on. Wait, so when you have the oblique asymptote, like when you do the long division and it gives you, let's say, x minus 4, then you have to do the opposite of it to have 4, right? And then you put...
You graph that line, x minus 4.
Mm-hmm.
That's it. You don't care what the remainder is. The remainder has nothing to do with the asymptote.
Yeah, but do you switch it? So would it be x cannot equal 4?
No, you don't. No. Okay. Remember that you can cross oblique asymptotes. So just because it's an asymptote doesn't mean x can't be that.
Okay.
And if I were to graph, let's say our oblique asymptote was x minus 4, well, that's the graph of x minus 4. It has a slope of 1, goes through a y-intercept of minus 4. So you always start your picture out with all your asymptotes. Okay. Now, Is this the one you wanted to do?
Yeah.
This is one of your problems? Okay. So do they ask any other questions? Do they want to know domain, range, x-intercepts, y-intercepts, any of that?
They just said, it just says to analyze each function, so I don't really know what they mean by that, but
Okay.
I mean, I guess that's what it was, finding the horizontal, vertical, and oblique asymptotes. I think that's what it was.
Okay, well, we still need to graph it. And
Okay.
typically, here, let me just graph a typical hyperbolic function. This is the elementary hyperbolic function. Okay? Vertical asymptote there, x can't be 0. Horizontal asymptote there because the power in the denominator is higher than the power in the numerator. We got a x to the 1 here. We don't have any x at all in the numerator. So I've got those two asymptotes, and the hyperbolic graph tends to look kind of like this. It certainly looks like that on this function.
Yeah.
Okay. Well, most functions that end up with vertical and horizontal asymptotes have hyperbolic appearance. So we're expecting to see something. If I were to guess without any information, I'm going to put one there. Probably going to put the other one here. And then what happens in between these asymptotes is typically it's either going to do that or it's going to go up and turn around and come back down. And then maybe this part would be up in that left quadrant.
Okay.
So the first thing we need to do is determine whether we ever cross the horizontal axis. And that will help us know whether or not we're going to cross here or go up and come back down.
Okay.
Well, in order to know the x-intercepts, we have to set y equal to 0 and see if we have a solution. If 0, in other words, x-intercepts occur when y equals 0, right?
Yeah.
Okay, so that has to be 0. What makes that 0? Is there a solution to that equation?
Well, you can try.
The only thing that matters is the numerator.
Yeah. Oh, the numerator.
The numerator has to be 0 regardless of what the denominator is. If I can make the numerator 0, then that whole thing's going to be 0. Because it doesn't matter what your denominator is. If your numerator is 0, the answer is 0.
Right, so it'd be -1.
-1, which means we do cross the x-axis right there. Because there is an x-intercept. And we're certainly not going to get an x-intercept from this part of the graph or this part of the graph. So we know it has to go through there. Okay?
Oh.
And
yeah.
That almost certainly means that the middle looks like this. Okay?
Okay.
And we can, let me think about this for a minute. That would mean that, you haven't talked about limits yet, have you?
I don't think so. I'm not sure.
Okay. Well, as x approaches -4, does this thing go to positive infinity? And you can tell that as x approaches -4, the numerator, if I were to just fill in -3.9 for x, and as it approaches, if I fill in the same -3.9, then that becomes +0.1. The numerator is -3.9 plus 1. Well, we can see that this number gets smaller and smaller and smaller. The whole result is positive, so the whole thing does approach infinity as we approach minus 4, which means this is the correct picture. Okay, in other words, as we approach 0, it's negative infinity. If you were to plug in like a negative 0.01 for x, you would find that this whole thing gets negatively huge.
Okay, yeah, I think we did that before.
Okay, so now the question is what, usually you can go right to left here, and if it goes up to infinity there, then you got to start on the other side of the asymptote at minus infinity. And if it goes up to infinity here, you got to start on the other side of the asymptote at minus infinity again. So this most certainly is the graph of it. But one last thing that you want to check is make sure that everything's in the proper quadrant. I call this the upper right quadrant. I call this the lower left quadrant. Well, as x is a positive number, everything's positive there. Okay, so that's the correct quadrant for that part of the hyperbolic graph. As x is less than negative 4, let's try a negative 5. That gives me negative 4 in the top, negative 5 times negative 1 in the bottom. That's negative. These two become positive. That's still negative. So we want to be below the y-axis, and we are. So now I'm 100% certain that we got the perfect graph. We're in the right quadrants. We checked a couple of points. We know what's going on in between because we go through the x-axis. If there was no solution for this, then you wouldn't cross this horizontal asymptote. It would just do something like go up and come back down. Okay. So that really is the way to analyze these graphs, is figure out your horizontal, your vertical asymptotes, and any intercepts. And y-intercepts would also be nice to know, but y-intercepts are where x equals 0, and we can tell right now there aren't going to be any because x can't be 0. You can never cross vertical asymptotes. So there can't be a y-intercept since x equals 0 is one of the vertical asymptotes. So once we know the x-intercepts, we know the quadrants, we know all of our asymptotes, then it's easy to draw the graph. And if you put this into your graphing calculator, you'd see something very similar to this.
Awesome.
Okay. All right. That's you just wanted a half hour tonight, is that right?
Yeah.
Okay. And you apparently have navigated my website because you figured out how to schedule this thing online. That worked out okay for you?
Yeah.
Okay. And I will just let you do that on your own. Is that the easiest way for you to do it, or do you prefer talking to me about it, or?
What do you mean? Is it the easiest way to do it, like, on this website?
Yeah, just to go to the website?
Yeah, definitely, yeah. Okay. I like to see it visually and everything. That definitely helps.
Good. Okay, well, I will let you talk it over with your mom and schedule your next session whenever you wish.
Awesome. Thank you so much.
Okay, Sonia. Thanks. Have a good evening.
You too. Bye-bye.